suppose this illustrates two parallel metal plates, and they're both neutral. What I'm going to do here, by some means, is I'm going to remove positive charge from the lower plate and place it on the upper plate. When I do that, the lower plate becomes net negative. And if I repeat that process, making the top plate positive, the lower plate becomes more negative as the top plate becomes more positive. It also becomes harder to do this, because in order to move a positive charge from this plate, don't I have to exert an electric force over a distance, so I'm doing work. So the energy that it takes to do that is going into electric potential energy, which you recall from a previous presentation, the electric potential energy divided by the amount of charge is always equal to a constant called the electric potential or the voltage. So the distance between these two plates, let's say, is D. I have to exert a force in order to move a positive charge from the lower plate to the upper plate. If I take that electric force and multiply it by D, that's the work done, which is equal to the electric potential energy on the upper plate. If I divide the electric potential energy by charge, and I divide the electric force multiplied by the distance by charge, we have that the electric field, Fe over Q, times D is equal to the electric potential energy divided by the charge, which is the electric potential. So we get that the voltage between the plates, or the electric potential difference between the plates, is equal to the electric field strength between the plates, which, remember, is a uniform field, multiplied by the distance between the plates. Now, what we have here is essentially a capacitor. It doesn't have the ability to recharge itself. If I would connect these two plates, we would have a flow of positive charge to the negative plate, and eventually the two plates would become neutral, and there would no longer be an electric field, of course, between them. So these plates can only hold so much charge. We say that it has a certain capacitance, which is measured in farads in honor of Michael Faraday. This is known as a capacitor, and the capacitance of a capacitor is equal to the amount of charge on one of the plates divided by the voltage between the plates, or the electric potential difference between the plates. The unit of capacitance is the farad. Okay, remember that the unit of charge is the coulomb, and the unit of electric potential is the volt. So a coulomb per volt is a farad. Capacitance is also equal to the area of one of the plates divided by the distance between the plates, multiplied by a constant, epsilon naught, which stands for the permittivity of free space, and kappa, which is called the dielectric constant. If, for example, we have air or a vacuum between these two plates, the dielectric constant is 1. these three equations can be used when working with capacitors. By the way, the human cell is a capacitor, and these equations can certainly be used. This is a capacitor, and this is a battery. The difference is that this is not capable of keeping its charge. It's basically just two metal plates separated by an insulator, whereas a battery has chemicals in it which allow the two plates in the battery to maintain a charge, okay, positive and negative. Okay, this right now is a neutral capacitor. If I connect it to the light bulb, you'll see that there is no charge on the capacitor. Whereas the battery, the light will stay lit indefinitely because a positive and negative charge are maintained, a voltage is maintained across the terminals of the battery, which means there's a continuous voltage drop across the light bulb, which is equal to the voltage rise given to the charge at the battery. Okay, now what I'm going to do is I'm going to charge up the capacitor, and to do that I can use the battery, or I could use a generator, which we'll learn about in a future unit. I could also use a Van de Graaff generator. That would be a little trickier though. So let me charge up the capacitor. And when it's fully charged, it will be at the voltage of the battery, which is about 6 volts. The capacitor should now be fully charged. I'm going to connect across the light bulb, and the capacitor will now discharge through the light bulb. Okay, what we have here is an RC circuit, a capacitance, a resistance, a light bulb, and a voltage source. Now when I close this switch, we're going to take a look at what happens, and the way we're going to take a look at what happens is by observing the light bulb. And then I'm going to sketch the graphs over here so you can see how the voltage across the light bulb, the resistance, the voltage across the capacitance, and the voltage across the entire circuit, and the current through the circuit varies with time. And then we're going to take a look at how the voltage across the resistance varies with the current as predicted by Ohm's law. We'll see if it agrees with the prediction that Ohm's law gives us. Okay, here we go. What you'll start to notice is that the light is getting less and less bright. So that means that the voltage across the resistance there is dropping. And it's an exponential decay that's occurring. And it looks something like this. The voltage across the capacitor, on the other hand, is increasing because charge is being stored there. And this is an exponential growth. Now, when you add the voltage across the resistance, which is dropping, to the voltage across the capacitance, which is rising, we should get the voltage of the source, the battery, from conservation of energy. The current across, or through, the resistance should also be dropping, and this too is an exponential decay. And in fact, it has the same shape as this curve up here, so that when we plot the voltage across the resistance as a function of time, we get a straight line as predicted by Ohm's law. The slope of this graph gives us the resistance. In this case, the resistance of the light bulb. Now, if we multiply the value of the capacitance in farads and the value of the resistance in ohms, we get time. And the unit is seconds. This time is called the time constant for the RC circuit, and it represents the time it takes the capacitor to reach 63.2% of its full charge. Now recall that the voltage across the capacitance is directly proportional to the charge on one of its plates. Therefore, this time also represents the time it takes the capacitor to reach 63.2% of the voltage of the source. What we're going to take a look at next is discharging a capacitor. Okay, here's a capacitor that is fully charged. Here's a resistance, and here's the switch. Notice I do not have a battery hooked up to the circuit. When I close this switch, let's take a look at what happens to the light. And then I will sketch the graph of the voltage across the light bulb, the resistance, the voltage across the capacitance, the voltage across the entire circuit, the current through the resistance as a function of time. And we'll also take a look at the voltage across the resistance as a function of the current and see if it agrees with that predicted by Ohm's law. Okay, here we go. Notice that the light started out fully intense. So the voltage across the resistance is reducing with time. The capacitor is also losing its charge, so the voltage across the capacitor is also reducing. Both of these are exponential decays. The voltage across the entire circuit would also be reducing, and this graph should look like the other two. The current through the resistance is also reducing. And since these two graphs look the same, then the graph of voltage across the resistance as a function of the current should be a linear relationship as predicted by Ohm's law, and the slope should give us the resistance. Once again, if you multiply the value of the capacitance times the resistance, you get the time constant, and this tells us the time it takes the capacitor to lose 63.2% of its full charge. It also means that this is the time it takes the capacitor to lose its original voltage by 63.2%.